Right, so first off, I'd like to apologize for this being late. For whatever reason, I was under the impression that it was due at 10 p.m., not 10 a.m. But anyway, for the first question, we have a position equation where we're supposed to find the time, position, and velocity when the acceleration is equal to 0. And first step is just to take the derivative of the position, which would give you the velocity, and then take the derivative of the velocity, which will give you the acceleration. And since a is equal to 0, we have this equation, and just using the quadratic formula, we can solve it for time. And once we solve for time, we can just plug time back into those two equations we solved for earlier, and we get negative 77 over 9 meters per second and 7 over 27 meters. For the second one, we have a bullet entering a medium. Initial velocity is 900 feet per second, and it goes in 4 inches deep before it stops, and the velocity is tracked by that equation there, and we are supposed to find the initial acceleration and time required to penetrate 3 inches. Knowing that the acceleration is equal to the derivative of velocity with respect to time, we have the derivative of velocity with respect to time of that equation there, which is acceleration is equal to negative k dx over dt. And then since dx over dt is just the velocity, we can plug in the velocity and then get the acceleration is equal to negative k times the velocity. And then since v is equal to dx over dt, we can use that to split the equation, and then we can take the integral of each side in order to find the time required, which ends up being 1 over k ln of VO over VO minus kx. And then since the initial velocity is 900 feet per second and it goes in 1/3 of a foot, we can just plug that in to the equation and find out what k is, to the initial equation they give us to find out what k is. And to find the initial acceleration, to find the initial acceleration, knowing that the initial velocity was 900 feet per second and k equals 2700 and x equals 0, we can just plug that into the acceleration equation and come up with negative 2,430,000 feet per second squared. And to find the time at x equals 3.9, we just use the time equation above and plug in all the variables, and we get 0.001366 seconds. Third one, a sailor drops a bowling ball into some water, and its initial velocity is 16.5 feet per second, and its acceleration is tracked with the equation a equals 10 minus 0.8 v, and it hits the bottom at t equals 3 seconds. And we're supposed to find the depth of the lake and the depth of the lake and the speed of the ball at the bottom. So first step is to just find the acceleration first step is, since acceleration is equal to dv dt, we can set a equal to dv dt in their equation, and we'll split and put the like variables together, and we'll integrate that, and then we'll solve for t, and eventually we will end up going through all the equation shown there. We'll end up with e to the negative 0.8 t equals 10 minus 0.8 v over 10 minus 0.8 vo. And since we know what v naught is, we can just plug that in, and we'll get a simpler looking equation for v. And then since we know that the ball hits the lake at t equals 3, we can plug that into the equation we found right there. You get 12.8 feet per second. That's how fast it hit at the bottom. And then after that, we know that the velocity is equal to the derivative of position with respect to time. So we can replace v in the equation with that, and we'll split the derivative again, and then take the integral of both sides. And then we'll end up with a position. And then you'll just need to plug in the numbers. Since t equals 3 at the bottom, we get x is equal to 42 feet. Okay, so number 4 is a runner and his movement's tracked by this velocity equation at x equals 0 and at t equals 0. We're supposed to find the distance the joggers run after an hour, and the acceleration at time equals 0, and the time at x equals 6. So first, we'll just knowing that the velocity is equal to the derivative of position with respect to time, we can replace v in the initial equation, put like variables together, integrate both sides, and then we will come up with this equation here. And then knowing that a is equal to the velocity times the derivative of velocity with respect to position, we can solve for the acceleration down here, and we'll come up with this equation over here on the right. And since we know that t equals 0 at x equals 0, we can just plug in those numbers and then come up with negative 0.675 miles per hour squared, or negative 0.000275 feet per second squared. And at the position x equals 6, all I need to do is plug into the time equation that x is equal to 6, and we'll come out with about 50 minutes. And at t is equal to 1 hour, all we have to do is plug in 1 hour, and then we can solve for x in the equation, and then we'll come up with like 7.15 miles. Alright, so 5, we're trying to find the escape velocity, minimum escape velocity of the particle, using the equation that acceleration is equal to negative g over r squared over little r squared. And so once again, we know that acceleration is equal to velocity times the derivative of velocity with respect to the radius. Knowing that, we plug that in for a, and we'll put like variables together, and then we will integrate both sides, and we will end up with this equation here. Since we know v is equal to O for r is equal to infinity, stated in the problem, we can just plug those in and come to the conclusion that c is equal to 0. And since c is equal to 0, the equation becomes this. And to find minimum escape velocity, we set r equal to r, since that's where we're trying to reach. And if we set r equal to r, we come up with this equation here. And then we just plug in the numbers, and then numbers that were given, and we end up with 11,180 meters per second. All right, so for the pulley problem, we want to model the length of the string here. You can model that with this equation here. And then since VB is going 2 feet per second, we can just plug in 2 feet per second and then realize that VA is equal to 6 feet per second. And since the length of the wire is constant, we can come up with this equation here. And since the weight is displaced 4 inches, we can just plug in 4 here. So the distance that block A moved is 12 inches. And using that same equation, but substituting in acceleration, trying to find acceleration with this equation here. Plug in the numbers, we get 18 feet per second squared. Using a similar equation to the above equation, but for block B this time instead of block A, we get, after plugging in the numbers, we get 6 feet per second. And then using the standard position equation and plugging in the numbers for A, we can find that A is moving 2 feet. And then since the velocity of A is equal to the standard velocity equation, we can just plug in the numbers for A and figure out that it's going 9 feet per second. Number 7. Number 7, a parachutist is in free fall. And it gave me 200 kilometers an hour. I just switched it to 55.6 meters per second up here. And we're supposed to find the time required for the parachute to land after opening his parachute and the initial deceleration. So we'll have to break this into its separate parts, and so we have from position 0 to position 1, from position 1 to position 2, and position 2 to position 3. I'll have to break it into all 3 parts and then solve for all 3 parts and then add them up at the end. So from 0 to 1, which is 14 meters, you just use the standard equation of motion and just plug in the numbers that it's given you from 0 to 1, and you'll find the acceleration. And then using the standard velocity equation, plugging the numbers it's given you from point to point, we have 0.4. And then do the same thing from 1 to 2. And then the same thing from 2 to 3. Pretty simple. And you add up all the times at the end, and you'll get around 44.716 seconds. Alright, so this one, we're giving the motion of a particle is equal to this equation here. And we're told that it's in a conic helix space curve, and we're supposed to find the magnitudes of velocity and acceleration. Alright, and since we know that velocity is equal to the derivative of the radius with respect to time, we just have to take the derivative of said equation, which ends up to be this. Since we're trying to take the magnitude and the magnitude is equal to square root of I squared plus j squared plus k squared. We square root all of them in sum of the squares, which will end up with this equation here. And since we know the trig identity, cosine squared x plus sine squared x is equal to 1, we can simplify it down to this right here. And similarly, since we know that acceleration is equal to the derivative of velocity with respect to time, all we have to do is take the derivative of the velocity equation, which will end up to be this. And then, like above, you just take the square root of the sum of the squares. And then also knowing that cosine x squared plus sine x squared is equal to 1, we can simplify that down to this. Oops. Number 9. A pitcher's throwing a ball, and we're supposed to find out if the ball meets a certain height requirement. And what the height of the ball is as it reaches the hitter. So this one's not too bad, just using a standard motion equation of velocity final minus velocity initial squared, both squared, is equal to 2g times the heights, total height. And just plugging in the numbers that were given. And since the initial velocity is VO sine 33 squared, just plugging in those numbers, we get a height of 3.5, which is in the range. So we're good there. And then a simple position equation. Using the simple position equation, we find that time is equal to 1.39 seconds. And then using a similar equation for position down here, but in the y direction, we can solve for the distance traveled in the y. So we know that the ball is about 1 meter high when it reaches a hitter. Alright. Number 10. At a halftime football game, souvenir balls are thrown to spectators with a velocity of VO. Determine the range and values of VO if the balls are to land at point A and point C. So first I wanted to find my zeros, and so this is where the ball was thrown from, is 0 and 2. And we'll want to find the initial velocity in the x direction and the initial velocity in the y direction. We can do that by these equations here. And the acceleration in the x direction is obviously 0, and the acceleration in the y is obviously negative g. Using the standard position equation and plugging in the numbers, we have the equation x is equal to VO cosine 40 degrees t. And then for y, we have y is equal to this equation here. And we're combining those two equations. And we can come to the realization that y is equal to this. And simplify a little bit, knowing that 1 over cosine x is equal to tangent x. We can come to a simple time equation. And then we just find xb, xy for the two different positions that are given. You just need to find where they are on the coordinate system. And this is where they are. After you find where they are on the coordinate system, it's simple to just plug in those numbers and you'll come up with a time from the time equation we solved for. And then using v naught times t is equal to x over cosine 40, which is a relation we found up here. We can just plug in the numbers that we got, including the time, and then find the initial velocity needed to reach that point. Alright, 11 and 12 are pretty similar. Both just using the equation acceleration is equal to v squared over r, and pretty much just plugging in the numbers that were given in the question statement. And then solving for the unknown that's there. It's pretty simple. So 11 is 2.13 meters per second, and 12 is 1,468 meter radius, minimum radius. All right. 13. We are given a plane is a certain distance away from a radio tower. We're supposed to find r dot, r double dot, theta dot, and theta double dot. First step you'll need to do is figure out r, because it's not given, but you can figure it out. It's 30,000 feet. And you can find theta from that, just some simple trigonometry. And since we know that velocity is equal to velocity of the radius times e of r plus velocity of theta times e of theta, we can derive these few equations for velocity. And then just plug in the numbers that we were given to solve for the velocity of the radius and the velocity of theta. Using those equations we were given earlier, we can come to the realization that theta dot is equal to v theta over r. And knowing that, we can solve for theta dot. Like the two problems before, acceleration is equal to v squared over r. Just plug in numbers, we can find the acceleration is 40.43 feet per second. And then adapting that earlier equation to acceleration instead of velocity, we realize that acceleration is equal to ar cosine theta plus a theta sine theta. And since we know all those numbers, we can plug them in. And we realize that AR is equal to 32.26 and A theta is equal to 26.34. taking the derivative of the earlier equation, we have this. And from that we derive these two other equations. And then we can solve for r double dot. And then we can also solve for theta double dot. Number 14 is just another block problem, a pulley block problem, and it can be modeled as this first equation here. And we can just, from that first model, we can get the velocity model and the acceleration model as well. And using the simple velocity equation, we can plug in our numbers and find out that block B is going 240 millimeters per second squared downwards. And then since it's going 240 millimeters squared downwards, and AC is going 75 millimeters per squared downwards, we can plug that into the equation into the acceleration equation, and then find the acceleration of A. And using the simple velocity equation once more, we can find the velocity of C, initial velocity of block C. And so now we know the initial velocity of block C and the initial velocity of block B. We can plug those in and find the initial velocity of block A, which is negative 43.33 millimeters per second. And if we want to find the distance, since the length of the rope is set, we can use a simple position equation. Plug in the numbers and you can figure out that it's going 727.5 millimeters to the right. Thank you.